Okay, guys, we'll see about today continuous charge distribution. Okay, so far we know how the charges are distributed. So, what is meant by continuous system of charges, right? So, always the scientists observe one charge. ஓகேவா ஸோ ஒரு சார்ஜ் எடுத்து அப்சர்வ் பண்ணுவாங்க அதுக்கப்புறம் என்ன பண்ணுவாங்க ஃபுல் அண்ட் ஃபுல் அதை வந்து அப்ளை பண்ணுவாங்க டோட்டல் சிஸ்டம்க்கு இப்போ டோட்டல் சிஸ்டம்னு எடுத்துட்டிங்கன்னா என்னது அதுதான் வந்து உங்களோட n நம்பர் ஆஃப் சார்ஜஸ் அதில் இருக்கும் சரியா n நம்பர் அப்படின்றது நீங்கள் எடுத்துருக்கிற டைமென்ஷனை பேஸ் பண்ணி ஓகே ஸோ இப்போ நம்ம வந்து என்ன பண்ணுறோம்னா கண்டினியூஸ் சார்ஜ் டிஸ்ட்ரிபியூஷன் இதில் எக்ஸ்பிளைன் பண்ணியிருக்காங்க யூ மஸ்ட் டேக் அ நோட் ஓகே இப்போ நான் சொன்ன மாதிரி நிறைய சார்ஜஸ் வந்து அதில் இருக்கும் ஓகே ஒரு கண்டக்டர் எடுத்துக்கிறீங்க திஸ் இஸ் அ கண்டக்டர் வேர் இட் இஸ் அ வயர்டு கண்டக்டர் ஓகேவா ஸோ இந்த கண்டக்டரோட லென்த் வந்து இன்ஃபினிட்டா போயிட்டு இருக்கு இப்போ ஃபார் எக்ஸாம்பிள் நீங்க இபி லைன் பார்த்தீங்கன்னா அந்த இபி லைன் எப்படி போயிட்டு இருக்கு ஸோ இன்ஃபினிட்டா போயிட்டு இருக்கு இந்த ஃபியூ கிலோமீட்டர்ஸ் இட் வில் ரன் ஓகே ஸோ அந்த மாதிரி ஒரு கண்டினியூஸா போயிட்டு இருக்கிற ஒரு லைன்ல எப்படி சார்ஜஸ் நம்ம வந்து மெஷர் பண்றது சார்ஜஸ் எப்படி நம்ம வந்து குவான்டைஸ் பண்றது தட் இஸ் வாட் கால்ட் சார்ஜ் டென்சிட்டிஸ் ஓகே ஸோ ஃபர்ஸ்ட் ஆஃப் ஆல் யூ மஸ்ட் அண்டர்ஸ்டாண்ட் லீனியர் சார்ஜ் டென்சிட்டி okay take the heading as linear charge density okay so it is defined as the charge you are just learning along with me right now இப்பவே படிச்சிடுறீங்க அவ்வளவுதான் okay after that you will give revision then it is easy for you so charge per unit volume okay so what is charge per unit volume linear charge density okay it is characterized sorry unit length sorry not volume it is charge per unit length charge per unit length okay see what is the length we have calculated unit length means for a continuous charge distribution you know about the differentiation right what is meant by differentiation so you are categorizing the differentiation of a function or a continuous function you are taking continuous function it is going on like that okay you are taking some part into the observation that is x and y axis into the frame of reference and then you are taking a small portion of it okay that means this small portion it represents little difference in y axis say y1 and y2 and little difference in x axis say x1 and x2 so what is the slope here the slope is y2 minus y1 by x2 minus x got it so that means difference in y axis by difference in x axis so the slope is nothing but it is the differentiable part we are differentiating the continuous element into a small elements so you are differentiating into a small elements like that we can differentiate so far so many elements are in between so it is differentiated so far and then we can sum all the differentiable quantities so that will give you integration that is the integral part okay so what is differentiation for a continuous thing for a continuous function you are breaking the continuous function or you are differentiating a continuous function into a small one okay and then it will be I mean getting differentiated further and then until it limits okay so then if you add all those differentiable quantities that will give you the integration is nothing but sum of all the differentiable quantities okay take a note of all these things with this idea only you are going to see what is line charge what is surface charge what is volume charge okay so we are taking this line charge density, right? What is the continuous charge distribution we saw? We saw the linear charge density, right? The charge is distributed continuously. So you have taken a small element that is delta L. Can you able to understand? Delta L is the small element out of total length. Okay, what is delta L? Small element out of total length. Got it? So delta L is the small element. Okay, where it stands from L2 minus L1. Like that we can take. I told you, if you keep this in a frame of reference, then you can able to understand the small change in X by small change in Y. So that is delta L. Clear? So what is the delta L? It represents, it is a small element of a total length, and you are taking Q number of charges are passed through the total length. Okay. So if there are Q number of charges, then you have to differentiate charge also. That small charge element will be delta Q. Okay. So what is this? Delta Q by delta L will be the linear charge density. It is designed by a letter lambda. It is given a letter lambda to explain delta Q by delta L. Can you take this? What is lambda? Lambda is the linear charge density. It is characterized by delta Q by delta L. So can you all say the unit? What is the unit? Delta Q is the unit. What is the unit for delta Q? Coulomb, right? What is the unit for delta L? Meter. So Coulomb per meter. So you can write the dimensional formula also. What is the dimensional formula? What is the dimensional formula for Coulomb per meter? For Coulomb, what is the dimensional formula? For Coulomb, I will explain you with this. Current is equal to Q by T. In lower classes, you have learned, right? What is the current? The amount of charges flowing per time. So that is current, Q by T. Okay. What is Q now? Coulomb. What is time now? Per second. Okay. So then you can include this. What is the unit for current? It is ampere. So ampere second is the coulombs, another unit. It can be expressed in terms of. So from this you can write the dimensional formula. What is the dimensional formula? It is not given in your book, but you can take it down. So dimensional formula is ampere, time, and meter inverse. Clear? Like that, we'll continue with the surface charge density. Put a heading as surface charge density. You have taken a long wire. After that, a very lengthy surface, 2D. Okay, first is 1D, next is 2D. You can mark 2D like surface charge density, put the heading as, it is defined as charge per unit area. Do write. It is defined as charge per unit area, and it is characterized by a letter sigma. Sigma is equal to delta Q by delta A. Sigma is equal to delta Q by delta A. So it is Coulomb per meter square it is. So what is the dimensional formula? For Coulomb it is ampere second time, and meter square L power minus 2. This is the dimensional formula. Okay. So SI unit is Coulomb per meter square. Then what is the third one? Volume charge density. Third one is volume charge density. It is characterized by letter rho or HO. This is rho, this is sigma. That is lambda. This is lambda. Okay. And then it is denoted by the unit Coulomb per meter cube. It is volume, right? So Coulomb per meter cube. And then what is the dimensional formula right now? A time and then L power minus 3. Okay. So now we are going to see the electric field due to continuous charge distributions. Okay. Very carefully you have to examine this. The field due to continuous charge distribution, it is given in this book. Suppose a continuous charge distribution in space has a charge density rho. You have taken a rho. Rho means volumetric, right? Choose any convenient origin. I told you, for every distribution, for every continuous distribution, you have to choose the frame of reference or the origin. Frame of reference or the origin. Otherwise, you can't define. Okay, it is not defined under the vague thing. Okay, so you have to confine it into a origin. So that in that origin, you can take 1D, 2D or 3D also. Okay. So right now, it is given that the position vector of any point in the charge distribution be R. So the same which is given here. So position vector means you have seen in force. System of charges, right? Coulombic force due to the system of charges. So you have seen there in this. So in the Coulomb's law, here comes, yeah. This is what? The position vector. So they have chosen a origin here. This is an origin. Got it? From the origin, you have to represent all the charges. Here it says Q1. Okay. Then Q2. Then Q3, Q4, Q5. Like that it will be. Okay. So this is the origin. You can already know it. So always the origin has to be set. Okay. So O to Q1 is the position vector R1. O to Q2 is the position vector R2. O to Q3 is the position vector R3. It can be expressed in terms of 2D, 3D, 1D also. Suppose if it is 1D, you can represent this vector as xi cap. Okay, if it is 2D, R1 vector can be expressed in terms of xi cap plus yj cap. If it is in 3D, then it will be xi cap plus yj cap plus zk cap. That we have learned already in the mechanics. Okay, is it clear for you this? So this is how you can confine the charge distribution in 1D, 2D and 3D. That is linear charge density, surface charge density and volumetric charge density we saw. Okay, so right now this is the basic idea you need to understand for this. Okay. Okay, then the charge density rho may vary from point to point, that you know, right? So it is not uniformly distributed. We couldn't say, okay, at one point the charge density may vary from another point. So it is a function of R. This also you know, right? All are represented by the position vector. Divide the charge distribution into small elements of size delta V. The change in the volume element is rho into delta V, right? Okay, that and all you know. Then now consider any general point. Always make sure if you want to find out the electric field, okay, you have to consider one point. Okay, so you are considering any point. At that point, the point P is definitely outside the distribution. That is, make sure it should be outside. Then the electric field due to the charge. Now, what is the charge? Delta Q is the charge. You know that volumetric charge density is delta Q by delta V. If you multiply rho into delta V, that is delta Q. So, in the place of delta Q, what is the electric field expression? Q by 4 pi epsilon naught R square, right? In terms of vector also you can represent. Suppose if the electric field is for the small element, then it will be delta E, it will be delta Q. So this delta Q can be written in terms of volumetric charges. Can you able to understand? That's it. So it is given here. Likewise, you can sum, I told you no. So summation over all the differentiable quantities. That might be expressed in terms of integration as well as summation also. Here you can write one more tip also. So what is this delta E? It can also be represented by dE Sometimes you will be given in questions. Okay, instead of delta E, it will be dE vector. Don't forget to write the vector symbol. 1 by 4 pi epsilon naught. It will be dq by r square r cap. Okay, got it? Suppose if it is, this is for small element. Okay, it is accountable for throughout all the surface, throughout all the volume, total volume. Okay, if you consider for total volume, it is differentiated into small volume, small volume, small volume, and every volume should be added up. Okay, that it meant to be summation over all delta V's, it says. Okay, so or else we can write E vector is equal to, okay, 1 by 4 pi epsilon naught integration. You can put the integration symbol. This integration is volumetric integration. So del dq by r square into r cap. Like this also you can represent instead of the summation. Okay. So in a strict mathematical method, we should let delta V approaches to 0. That and all we saw. Since instantaneously, you can take a very small value. Okay. Okay, guys, I will change. I will change it to red. Okay. Okay. Is it clear now? Right now, can you able to see? Okay. I think Kavya, you can able to see this. Red color is okay. Okay. Then finished up. This is all about the electric field due to your continuous charge distributions. Okay. So you know about electric field due to a point charge. We saw, right? All if you take down this notes, then we'll move on to the Gauss law. Take down electric field due to a point charge. So electric field due to point charge will be characterized by the letter E cap, E vector is equal to 1 by 4 pi epsilon naught into Q by R square. This is the point charge. Simple, we can write. Okay. So, you know, there is a, or else in your book it shows capital Q. Okay. So capital Q, once I repeat, capital Q is at one place and then you are bringing the test charge, right, to one point. It is the test charge Q. Okay, or Q naught, whatever it might be, you can take. So this is the distance between this point and the source charge. Yesterday I taught you, and this will be the force due to this Q, right? What is this Q? This Q is exactly the unit test charge. This is source charge. So once again, I repeat, it is nothing but electric field due to a point charge. Okay. If Q is negative, then you know the E is directed towards Q. Okay, well, if it is negative, how can you write if this is for force vector? Have you all taken down this? I will explain you in this. Suppose for a electric field, okay, I will explain you this. With this source charge Q. This is source charge, and then actually